This video is about the reactions of ozone, why it's important in green chemistry, and some of the more difficult mechanisms involved in ozone production and ozone depletion. So first of all, where is the ozone layer? Let's have a look at Earth. This is not to scale particularly. The atmosphere is very, very, very thick, as you can see. We're looking at 50 kilometres above the Earth's surface. The atmosphere is split into layers, so the layer that's closest to the Earth is called the troposphere. If you do biology, you might have heard of things like trophic levels, trophisms. We're looking at, this is the area where life exists. Above that, in the stratosphere, think of stratospheric being something that's going very high, you've got the ozone layer. So it's above the troposphere, it's above the area in which we are generally living, birds flying, etc. So what is ozone and why is it important? Ozone is a very unusual molecule. It's composed of 3 oxygen atoms bonded together. If you were to try and draw a dot and cross diagram of ozone, you would have some difficulties. Really, it's a molecule in which the 3 oxygen atoms are joined together by single bonds, and then there are some electrons which are actually delocalized across the 3 oxygen atoms. And so therefore it's kind of flipping between a double bond and single bond situation. How is ozone formed? It's not often formed at this level in the troposphere. Very few times will you get ozone formed because it requires energy to do so. First of all, you need to take normal oxygen and break it up. In the stratosphere, this happens because UV light is absorbed. UV light could be absorbed in the troposphere as well by oxygen, but in the stratosphere, where it's much, much further out and closer towards the sun, there's a much higher intensity of UV light. On absorbing the UV light, the oxygen molecule is able to split into 2 oxygen atoms, which are radicals. That oxygen radical, if it then collides with another undissociated oxygen molecule, will form ozone. So, it may not have occurred to you, but how are oxygen atoms radicals? Because oxygen is in group 6. And we've been told that radicals are species which contain unpaired electrons. So oxygen does not have an odd number of electrons in its atoms. Well, here's a dot and cross diagram of an oxygen molecule. And here's what happens. This is how you should draw an oxygen atom if you were to draw a single oxygen atom. You may have been conditioned to draw an oxygen atom like that, even from as early back as GCSE, and not really understood why you're doing it. But it's pretty easy to explain when you look at the S and P configuration of an oxygen atom. You know that there are 6 electrons. This means that there will be 2 in the 2s orbital. In the 2p subshell there are 3 orbitals, which means that the 4 electrons, 2 of them, will be unpaired. So an oxygen atom is in fact called a biradical. It has got an even number of electrons, but that just means that 2 of them are unpaired. So back to the ozone layer. We've explained how it forms. What's the point of it? Why is it so important? Well, ozone molecules also absorb UV light, because as we said, there's a lot of it about in the stratosphere. Very high intensities. When it does this, it splits back up into oxygen molecules and oxygen radicals. Again, this is all seeming pretty pointless because we've just said that ozone is formed by the reverse reaction, oxygen molecules reacting with oxygen radicals. So why do we care that it is being formed and broken up? The reason we care is because this particular wavelength of ultraviolet light that is absorbed only by the ozone molecule is the most harmful wavelength of ultraviolet light. And this process of oxygen forming ozone, and ozone then absorbing ultraviolet, is really responsible, in fact, for the evolution of life outside of water on Earth. Before the ozone layer, before plants produced enough oxygen to produce the ozone layer in the stratosphere, life could not live outside of the water because the UV levels would be so high that DNA mutation rates would be way, way, way too high. So what have we done to the ozone layer? We've introduced CFCs. CFCs are chlorofluorocarbons. They're compounds that are based usually on methane, but instead of having hydrogen atoms, they have fluorine and chlorine. So something like this. This would be dichloromethane. Why did we develop them? What was the point? This man is Thomas Midgley. Have a good look at him. He is, let's face it, a pretty evil man. He's possibly responsible for the worst damage to the Earth's atmosphere a single human has ever inflicted. In fact, the first thing he did, before he developed CFCs, was to introduce lead compounds into petrol. We haven't had those for a long time now, which is lucky. In fact, in Thomas Midgley's lifetime, he learnt about the brain damage, and especially damage to young children, that these lead compounds were causing. He felt a bit guilty about that, and so he decided to develop some nice, safe refrigerant. Old refrigerants, before CFCs were developed, were toxic, they were often corrosive, and more often than not, they were also flammable. They were very nasty chemicals. So Thomas Midgley, feeling rather guilty about the lead situation, was helping to develop alternatives. CFCs were his crowning glory. They contain very strong carbon-halogen bonds, carbon-fluorine and carbon-chlorine. That means they're very, very unreactive, which means they're unlikely to be toxic, and they're very, very also unlikely to be corrosive. They're not flammable either, because of the strength of these bonds. In fact, Thomas Midgley did once demonstrate this by taking a massive lungful of his CFC compounds and blowing out a candle with it. The other point about CFCs is to be a refrigerant means that they have to be quite volatile. They turn into a gas quite easily and they liquefy quite easily because that's how refrigerants work. So, what happened then? We started using CFCs. They're great. CFCs, as we know, are extremely unreactive, which means that down in the troposphere, normal levels of UV light, nothing happens to CFCs. They last for years and years and years, and eventually, because they're very volatile compounds, they will make their way upwards and upwards until they get to the ozone layer. So what happens to a CFC when it gets to the ozone layer? Well, funnily enough, like everything else in the ozone layer, it's going to absorb some ultraviolet light. Ultraviolet light which is now present in much higher intensities than down in the troposphere. The higher intensities mean that the UV light here is going to be enough to break that very strong carbon-chlorine bond. The carbon-fluorine bond won't break because that really is a very, very strong bond. And so you will form two radicals, the CF2Cl radical, and the one that we're really going to look at is the chlorine radical. So the chlorine radical, as we know, radicals are extremely reactive species. If it collides with a molecule of ozone, then the first thing it will do is pull an atom off that molecule of ozone and leaving an O2 molecule behind. So it has destroyed that molecule of ozone. And it's done that without the ozone absorbing any UV light. So the UV light that the carbon-chlorine bond absorbed, that's not the same UV light necessarily, not the same wavelength that the ozone would have absorbed. The other thing you'll notice is that even though the chlorine has taken an oxygen atom away from ozone, it's still a radical species. because chlorine has 7 electrons in its outer shell and oxygen has 6. So overall there's an odd number of electrons there. So the ClO radical is quite likely to collide with a single oxygen radical, because remember there are a fair few oxygen radicals in the atmosphere, in the ozone part of the atmosphere, because they've been formed by oxygen splitting up under the UV light. If this happens, this means that the oxygen radical will remove the oxygen from the ClO radical. We'll get back our chlorine radical and produce a relatively stable O2 molecule again. So, why is this important? Well, let's look at the overall equations for those two reactions. You've got a chlorine radical reacting with ozone to make ClO and O2. You've also, elsewhere, then got the ClO reacting with an oxygen radical to make a chlorine radical and O2. These are obviously not the only collisions that will take place, as there are many, many different gaseous species up in the ozone layer. However, look at what happens if these two reactions take place alongside each other, which they're very likely to do. The chlorine radical is used up in the first reaction, but regenerated in the second reaction. The ClO radical is produced in the first reaction, but used up in the second reaction. So overall, in this part of the ozone layer, there's no change in the concentration of chlorine radicals. They're not used up. And the overall reaction is in fact ozone reacting with an oxygen radical to form 2 molecules of oxygen. The chlorine radical, therefore, is acting as a kind of go-between. It's acting as a catalyst for both the decomposition of O3, the ozone, and it's using up the oxygen radicals as well. So they're acting as a catalyst because the chlorine atoms, the chlorine radicals, are regenerated, they're unchanged at the end of the reaction. As well as breaking down the ozone, the O3, they're also removing the oxygen radicals, which, if you remember, they were needed to collide with the O2 molecules to create more ozone. So before CFCs and the chlorine atoms were introduced, there was an equilibrium between the breakdown and the production of ozone, which kept the concentration of ozone constant for many, many years. Chlorine radicals can catalyse this reaction typically 10,000 times before they're removed from the stratosphere. To be removed, they may diffuse away, or they may react with other species, which stops them from being radicals. They have had a devastating effect to the extent that when ozone was originally, levels of ozone were originally measured, scientists actually ignored the problem because they were so low, they actually assumed that there was a mistake in the instruments, that they couldn't possibly have changed that dramatically. We haven't used CFCs for a very, very long time since we've understood the implications of their effects on the atmosphere. So we have some alternatives to CFCs now. Most of them centre around containing weaker bonds. So they may contain one or more carbon-hydrogen bonds, or occasionally carbon-bromine bonds. The reason the weaker bonds are important, we actually want CFC alternatives to be more reactive than actual CFCs. If they're more reactive, then like just about every other compound, they'll react in the troposphere and break down into other compounds. So they won't reach the stratosphere, and they won't reach that point where they will absorb UV and form radicals. It's not the end of the story for ozone depletion, unfortunately, because we also have to look at the effects of high-flying jet aircrafts on the ozone layer. Some aircraft fly very, very high up, and inside that jet engine it is very, very hot. Now the jet is burning fuel such as kerosene, which is a hydrocarbon. Of course it's producing carbon dioxide and it's producing water. But as we said, it's also very, very hot in there. Inside the heat of a jet engine, this also happens in diesel engines and petrol engines, nitrogen and oxygen from the air are able to react to form nitrous oxides, such as NO, nitrogen monoxide. Here's a dot and cross diagram of nitrogen monoxide. Notice anything special about it? There it is. It's a radical molecule. So, nitrogen has 5 electrons in its outer shell, oxygen has 6. Overall, we end up with an unpaired electron. So nitrogen monoxide catalyses the depletion of ozone in exactly the same way as chlorine radicals. In fact, the reactions are identical, except for that instead of having a Cl, we're going to have an NO. So first of all, NO reacts with O3, takes off an oxygen and leaves O2 behind. In the second stage, NO2 that's formed in the first stage, that's a little bit like the ClO, because the ClO is Cl plus O, the NO2 is NO plus O. The nitrogen dioxide can react with oxygen radicals and it forms nitrogen monoxide. Here it is, it's replaced the nitrogen monoxide and it's catalysed the reaction of O3 and O to form 2 lots of O2. Notice that the oxygen species here, the O radical, hasn't got a sign to show it has an unpaired electron. That's not always going to be given to you in questions. You're not always going to be shown what is a radical and what isn't. Because let's face it, the NO, which we would normally just write as NO in an equation we've just established, is a radical. In fact, if I wanted to be really fussy, I'd have to point out that oxygen molecules are in fact biradicals also, and they end up with unpaired electrons. So, this is what's happening with aircraft at the moment, but it's nowhere near as bad as the problem with CFCs that we're still trying, even now, many, many, many years on from using CFCs to combat. I'll leave you on a positive note, which is that, firstly, Thomas Midgley never found out about the damage that CFCs did to the ozone layer. So he never found out that his dream compounds caused even more damage, and in fact many, many cases of skin cancer and death, compared to his addition of lead to petrol. If that doesn't cheer you up, then perhaps the way he died will. He had contracted polio and developed a contraction that helped him get dressed, and one day it went wrong and strangled him. The end.